You know, quantum mechanics has this reputation for being, well, weird, mysterious, even impossible to really wrap your head around. But what if one of its biggest puzzles, superposition, isn't actually mysterious at all? We're going to see how a simple shift in how we look at it can make the seemingly impossible suddenly completely intuitive.
So, it all kicks off with the most famous cat in all of physics, Schrödinger's cat. You've probably heard the idea, right? That until you actually open the box, the cat inside is somehow both alive and dead at the same time. This one thought experiment has basically become the poster child for just how bizarre quantum mechanics is supposed to be.
But here's the thing. The cat is really just a stand-in for a quantum particle. And this question, how can anything be in two totally contradictory states at the exact same time, has been haunting physics for 100 years. It seems to break the most basic rules of reality. But what if we've been asking the wrong question all along?
To crack this mystery, we don't need to wade through pages and pages of complicated theory. Turns out, the biggest clue has been hiding in plain sight this whole time, right there in the basic math of quantum mechanics.
Okay, so this is the standard way physicists write down a quantum state. Now, look, don't get hung up on the weird brackets or the Greek letters. All this equation is really saying is that our state is some kind of mix of two basic options. Let's just call them state 0 and state 1. And the amounts of that mix? Well, that's determined by those two numbers, alpha and beta.
And this is where it gets really interesting. There's this rule that physicists have always known. Whatever those alpha and beta numbers are, if you square them, they always have to add up to exactly 1. Now, this isn't just some random little rule. This is the crucial clue. It's like a mathematical flare, basically screaming at us, telling us what's really going on here.
So that clue? It leads us to a beautifully simple answer. The whole mystery of being in two states at once has nothing to do with magic or spooky quantum weirdness. It has everything to do with geometry.
All right, here it is, the big reveal. A particle in superposition isn't in two different states at all. It is in one single state, and that state is a vector, which is just a fancy word for an arrow with a length and a direction. And that rule we just saw, the one where the squares add up to 1, well, that's just the Pythagorean theorem you learned in high school, and it's describing a vector with a length of exactly 1.
You know, this simple compass analogy is what makes it all just click. Imagine a compass needle pointing straight north. You'd say it's in a pure north state. Same if it's pointing east. But what if it points northeast, like it is here? Is it pointing in two directions at once? No, of course not. It's pointing in one very specific direction, northeast. That direction just happens to have a little bit of north in it and a little bit of east in it. Superposition is just the quantum version of pointing northeast.
So what this does is it forces us to completely reframe how we talk about this. Superposition isn't being in multiple states at the same time. No, it's about being in one single geometric state that, just like our northeast vector, has components that point along different directions you might decide to measure. Now, physicists actually have a formal tool for visualizing this whole thing, and it's called the Bloch sphere. You can kind of think of it as the ultimate quantum compass. Every single possible state a quantum particle can be in corresponds to one unique point on the surface of this sphere. Let's use this sphere to get a feel for it, right? If our state vector is pointing straight up to the North Pole, that's our pure state 0. If it points all the way down to the South Pole, that's state 1. So what about anywhere along the equator? Well, that's a perfect 50-50 superposition. That's the quantum version of our northeast direction.
Okay, so if superposition is just a vector, what about that other big quantum mystery? The so-called wave function collapse. That spooky moment a measurement forces a particle to magically choose a state. Well, guess what? Our new geometric picture solves that too.
What we call collapse isn't some weird mystical event at all. It's just a sequence of really simple geometric steps. Step 1. The quantum state is a vector, pointing in some direction. Step 2. When you decide to measure it, all you're doing is defining an axis, like north-south. Step 3. The act of measuring is just projecting that vector onto your axis. And step 4. The result you get is just the length of that projection. That's it. No spooky action needed.
So get this, nothing is actually physically collapsing. The vector was always pointing in its one single direction. A measurement is simply the process of asking, hey, from my point of view, how much of you is pointing north? You're just pulling out the coordinate information from a geometric object that was already there. Now, I know this might all seem like just a neat little conceptual trick, but seeing quantum mechanics this way, as geometry, well, it has huge real-world consequences. This is the key that's unlocking some of the most advanced technologies being built today.
Think about it. Once you stop seeing a quantum bit, a qubit, as some weird paradox, and start seeing it as just a vector on a sphere, building a quantum computer suddenly becomes an engineering problem. How do you precisely control the direction of that vector? This also explains why quantum encryption is unbreakable. Any attempt by a spy to measure the state is just a geometric projection, which always changes the vector's direction, a disturbance you can always detect.
You know, the takeaway here is pretty profound. For a century, we've been telling these spooky stories about quantum mechanics because we were basically staring at shadows on a cave wall. But the moment you turn around and see the simple, geometric object that's casting those shadows, the whole mystery just disappears.
And that, right there, is the ultimate takeaway. The fundamental nature of our reality, down at the tiniest scales, isn't governed by paradoxes or magic. It's governed by the elegant, predictable, and, well, beautiful rules of geometry.
So it leaves you with this really fascinating final thought, doesn't it? If one of the biggest paradoxes in all of science turned out to be just a simple geometric idea we were looking at from the wrong angle, what other big mysteries, in science or even in our own lives, are just geometry in disguise, waiting for us to find the right perspective?